So what do you picture when you think of a continent? Probably something totally solid, ancient, unmoving, right? I mean, it's the very definition of terra firma. For literally billions of years, these huge landmasses have seemed like permanent fixtures on our planet. But what if that's not the whole story? What if the very foundations of our world are actually, slowly but surely, being pulled back down into the earth?
Yeah, the textbook idea is that continents are built on this incredibly tough, stable base. These are the parts of the Earth's crust that have survived everything the planet could throw at them for eons, acting as these steady shields where life could evolve. They're supposed to be, for all intents and purposes, geologically unbreakable. But as geologists are looking closer, they're realizing that this picture of perfect stability, it might just be an illusion. They're finding out that the very bedrock of our world might have a secret. And, get this, a surprisingly dynamic life of its own. To really get this, we need to introduce our main character, the Craton. A Craton isn't the whole continent, but it's the ancient, tough-as-nails core. We're talking about these immensely old and thick pieces of the Earth's lithosphere that have just sat there, stable for billions of years, resisting all the churning from our planet's interior. They are the continent's super strong foundations. And yet, we've got some geological crime scenes that just don't add up. Take the North China Craton. Everyone thought it was indestructible, but back in the age of dinosaurs, it mysteriously thinned out and was hit with all sorts of earthquakes and volcanoes. Or look at the Wyoming Craton, right here in North America. Parts of it are literally being worn away from underneath. This stuff isn't supposed to happen to a Craton. So, this brings us to the big mystery. What force on Earth is powerful enough to break down these supposedly unbreakable continental cores? How do you kill a Craton? Well, scientists are tackling this question from two pretty incredible angles. First up, if you want to understand how something breaks, what do? You build a copy and you stress test it. In geology, that means firing up the supercomputers to basically recreate the scene of the crime. Researchers like Shannon Connor and her master's thesis did exactly this. They built a virtual model of the Earth's mantle, plopped a Craton on top, and then, and this is the key part, they put a little weak zone inside it. Think of it like a geological Achilles heel. Then they just let the simulation run to see what would happen under all that immense pressure and heat of the deep Earth. Okay, this slide shows so brilliantly what they found. What we're looking at are 4 different simulations, each playing out over millions of years. The purple block is our stable Craton, and that green bit is the weak zone we were just talking about. Now, the only thing they changed in each row is the weak zone's viscosity, which is just a fancy word for how resistant it is to flowing, how runny it is. Just watch what happens as the viscosity goes down from the bottom to the top. That weak zone stops acting like solid rock and starts to stretch, tear, and get pulled away by the churning mantle down below. It's wild. So these simulations basically showed 3 possible fates for a weakened Craton. Sometimes it manages to hold itself together. Other times, it just splits clean in two, like it's being ripped apart. And in the most fascinating scenarios, pieces of its foundation they drip away. This chart pretty much sums up dozens of these computer simulations. Each little symbol tells us what happened. Circles mean the Craton stayed intact, stars mean it split, and triangles mean it dripped. Now just focus on that vertical line on the left. That's viscosity. High viscosity is at the bottom, low is at the top. See the pattern? Almost all the circles, the intact Cratons, are clustered down at the bottom where viscosity is high. And almost all the drips and splits, they're up at the top where the viscosity is low. It's a dead giveaway. So the huge takeaway from all these models is this. It's not really about density or heat or even how big the weakness is. The single most important thing that decides if a Craton lives or dies is viscosity. If you can somehow make its foundation less viscous, weaker and more like a fluid, it's gonna fall apart. Okay, so that's a really powerful theory based on some amazing computer models. But is it just a digital ghost story? Or can we actually see this happening somewhere on Earth, right now? For our second line of evidence, we're going to move from simulation to surveillance. Geologists are now using the planet's own vibrations to get a live look at what's going on hundreds of kilometers right under our feet. So how do they do this? They use a technique called seismic tomography, which is basically a CAT scan for the entire planet. See, every earthquake sends seismic waves ringing through the Earth. By tracking how fast those waves travel, scientists can map out different types of rock deep in the mantle. It's kind of like using sound to see in the dark. And using this technique, scientists have made a discovery that is, well, it's absolutely stunning. They have actually seen what the computer models predicted. Portions of the ancient North American Craton are, right now, peeling away and sinking down into the mantle. It's happening as we speak. And this isn't ancient history. This is active geology. Deep beneath the American Midwest, the base of the continent is literally being removed. So what's causing it? Well, the likely culprit is the ghost of an ancient oceanic plate, this thing called the Farallon Plate that slid under North America millions of years ago. As its remains sink down into the mantle, they're stirring up currents that are now eating away at the continent from below, which is almost certainly reducing its viscosity, just like the model said it would. So, let's step back. We now have two incredibly powerful lines of evidence. We have the how from the models, and we have the what from the real world. Let's put them side by side and see what we've got. On one hand, the computer models gave us the physics. They showed us how a craton could be destroyed. You lower the viscosity of its foundation, and it starts to drip and split apart. Then, the seismic imaging came in and provided the real-world proof. It showed us that this exact dripping process is happening right now, deep beneath North America. The theory and the observation, they match perfectly.
So with all this, we can now map out the entire life cycle of a continent's foundation. For billions of years, it can be totally stable, but then some geological event, like a plate sliding underneath it, can start to weaken it from below. Over tens of millions of years, this weakening lowers its viscosity until eventually parts of it just detach and sink, recycling that ancient rock back into the deep earth. The big picture here, the really crucial insight, is that continents are not the permanent, unmoving things we always thought they were. They're actually active players in this planet-scale recycling system, this epic, slow-motion cycle of creation and destruction that plays out over hundreds of millions of years. As Professor Thorsten Becker puts it, this new understanding is absolutely fundamental. It helps us answer some of the biggest questions in geology. How are continents born? How do they die? And how does their ancient material get reborn into the Earth's mantle? And it all comes back to that key insight we got from the computer models. Sure, other things like density play a role, but viscosity has by far the highest impact. It's the master variable controlling the fate of a continent's foundation. You change the viscosity, you change the world. Now, before you start worrying about the ground opening up beneath your feet, let's just remember the timescale we're talking about here. This is not a disaster movie. This is the slow, patient work of geology, playing out over 100 million years, or more. Our continents have been around for a long time. And this all leaves us with fascinating final thought. We now see the Earth not as this static ball of rock, but as this incredibly dynamic system that's constantly remaking itself. So if old continents are being slowly unmade and pulled back into the mantle, what new structures is our planet quietly and patiently building for the future?